There is a moment, somewhere in the middle of the Masai Mara, when the savannah stops being a backdrop and starts being a thing that breathes. You feel it before you understand it. The grass moves and it is not the wind. Something shifts at the edge of your vision, and by the time your brain has processed what you saw, the thing has already happened. And in this particular story, what happened lasted less than 4 seconds, covered roughly 60 meters, and ended with a margin of survival so thin that it barely qualifies as a margin at all. A zebra outran 3 lions by a distance that in any other context would not even be worth measuring. A few inches, the length of your hand, the difference between being alive and being something else's meal measured in the width of a lion's paw. And when you actually sit with that, when you let yourself understand what had to go right in those 4 seconds for that zebra to still be breathing, your entire understanding of what an animal body is capable of shifts in a way that does not shift back. Subscribe right now if you want to understand what survival actually looks like, not the version that gets narrated over slow-motion footage with dramatic music, but the real thing, the biological thing, the thing that happens at the edge of physics and reflex and years of muscle memory and a nervous system that was built specifically for this moment. Let's get into it. To understand what happened to this zebra, and I mean really understand it, not just watch it and feel the adrenaline but actually comprehend what was happening at a mechanical and biological level during those seconds, we have to start somewhere that seems a long way from the Mara. We have to start with what lions are, not what they look like, not what they symbolize. What they actually are as hunting machines, because until you understand the predator, you cannot understand what surviving the predator actually requires. A lion is not the fastest thing on the savannah. That surprises people because lions look fast, they feel fast, the idea of a lion is fast. But a cheetah reaches 112 kilometers per hour. A lion tops out at around 80, which is still faster than any zebra. A zebra's top speed is somewhere between 65 and 80 kilometers per hour depending on the individual animal, its condition, the terrain, and a dozen other variables. So on a straight flat track, a lion and a zebra are close to matched, with the lion potentially having a slight edge in pure top speed. But lions almost never hunt on a straight flat track, and that is not the point anyway because lions do not win by being faster than their prey in the final sprint. Lions win by not having to sprint far at all. The lion hunting strategy, refined over millions of years of evolution in the specific ecological context of African grasslands and savanna, is fundamentally a strategy of position. It is a strategy of reducing the distance that needs to be covered between the predator and the prey to the point where speed becomes almost irrelevant, where by the time the prey knows the attack has started, the attack is almost over. The ambush, the stalk. The slow, patient, neurologically expensive business of moving a 200-kilogram body through grass without making the kind of noise and visual disturbance that a 200-kilogram body naturally makes. This is what lions are brilliant at, not the sprint, the approach. And this is why 3 lions working together changes the mathematics of survival so dramatically. Because now we are not talking about one ambush point. We are talking about three positions, 3 sets of eyes tracking the herd, 3 bodies that can be placed at different angles relative to the target, creating a geometric trap that eliminates safe directions of escape one by one. The coordination of a lion hunting group, called a coalition in males, a pride in the broader social sense, is not sophisticated in the way that wolves or killer whales are sophisticated. Lions do not have elaborate pre-hunt tactical planning. But they have something almost as effective, which is the accumulated behavioral knowledge of animals that have spent their lives watching each other hunt, that have developed through experience an intuitive sense of where the other hunters are likely to be, and that use each other's presence and movement as information in real time during a hunt. When one lion makes a move, the others respond to it. When prey breaks in one direction, the lion on that flank is already reading the geometry. It is not communication in the way we understand communication. It is something more visceral and more immediate than that. It is 3 nervous systems that have been hunting together long enough to have learned to function as parts of a single strategy without any of the 3 needing to consciously formulate what that strategy is. This is what the zebra was running from, not just 3 fast animals. 3 fast animals whose positions and movements were creating a narrowing envelope of possible escape routes in real time, each second that passed making the geometry slightly worse, the options slightly fewer, the margins slightly thinner. Now let us talk about what the zebra is. A plain zebra, Equus quagga, is not the animal that most people fully understand when they look at it. Most people see the stripes, which are extraordinary and which we will get to, and they see a horse in a striped coat, which is close but not quite right in a way that matters enormously for understanding what happened in those 4 seconds. A zebra is not a horse. It is related to horses. It shares the same genus order. It is recognizably equine in its body plan, but it has been shaped by a completely different evolutionary history in a completely different landscape with completely different predators. And the differences between a zebra and a horse, specifically the differences that are invisible, are precisely the differences that keep zebras alive in a landscape that would kill a domesticated horse very quickly. The first thing to understand about zebra musculature is that it is built for a different kind of work than horse musculature. Horses, particularly domesticated breeds, have been selectively shaped over thousands of years for sustained speed in a particular direction on flat terrain, the kind of performance that makes them useful for racing and for cavalry and for pulling. Zebras have been shaped by the necessity of surviving ambush predation in variable terrain, which requires a different set of physical capabilities. Yes, top speed matters, but so does acceleration from a standing start. So does agility at high speed. So does the capacity to change direction sharply without losing momentum catastrophically. So does the capacity to sustain effort not for a quarter mile on a track, but for however long it takes to get far enough from a predator that the predator abandons the chase. Zebra's hindquarters are massively powerful, built for the explosive initial acceleration that turns a grazing animal into a projectile in under a second. The kicking force that those hindquarters generate is also not incidental. A zebra kick has been measured at nearly 3,000 newtons of force, enough to break a lion's jaw or skull, which means the hindquarters serve a double function as both propulsion system and last resort weapon. The legs of a zebra, like all equines, have evolved to be extraordinarily efficient structures, with much of the musculature concentrated high up near the body and the lower leg consisting largely of tendons and bones that act as springs, storing and releasing energy with each stride in a way that reduces the metabolic cost of running and allows sustained high-speed movement far longer than a purely muscular system would permit. The zebra's hooves are another critical element. Hard, impact-resistant, shaped for traction on the kind of varied terrain that the Mara presents, from dry hard-packed earth near the river crossings to loose sandy soil on the open plains to the slick mud of the wet season. The hoof of a plains zebra is specifically adapted to the African savanna in a way that gives it traction on surfaces that would be treacherous for a less adapted animal. And in a chase that might cross several different terrain types in the space of a few seconds, that traction is not a minor advantage. It is the difference between a clean stride and a slip that costs a tenth of a second, and in a race decided by inches, a tenth of a second is everything. But the most important thing about a zebra running for its life is not any single physical attribute. It is the integration of everything happening at once. The sensory system that detected the threat and triggered the response. The nervous system that converted detection into movement in a time interval so short it barely registers as time. The musculoskeletal system that executed the movement with the precision and power needed. The cardiovascular and respiratory systems that flooded the muscles with oxygen in the first seconds and then sustained the effort. The brain doing dozens of things simultaneously, tracking its own body through space, processing sensory information about terrain and obstacles and the positions of the predators and the positions of the other zebra in the herd, making the constant micro-adjustments of direction and speed that turn a straight-line sprint into something much harder to predict and therefore much harder to intercept. And there is the herd itself, because this zebra was not running alone. The behavior of a zebra herd under predator attack is one of the most studied and still most incompletely understood phenomena in behavioral ecology. The immediate visual effect is what most people have seen in footage: chaos, the herd exploding in multiple directions, animals scattering in what looks like panic, a confusion of stripes moving at high speed, but it is not random. Or rather, it is random in exactly the way that makes it most effective as a predator confusion strategy. And the difference between random chaos and strategically effective chaos is not something that is easy to see with the naked eye. The stripes are the key to this, and the story of why zebras have stripes is one of the most debated questions in evolutionary biology, with multiple hypotheses competing and none of them fully resolving the question, which means the actual answer is probably some combination of several of them. The thermal regulation hypothesis suggests that the alternating black and white stripes create microairflows close to the surface of the skin, as the two colors absorb and radiate heat differently, creating convection currents that help cool the animal. This is supported by some physical measurements of temperature differentials between black and white stripes, but is contested in terms of whether the effect is large enough to be evolutionarily significant. The fly avoidance hypothesis, which has received substantial experimental support, suggests that the stripes disrupt the polarized light patterns that biting flies use to identify suitable landing surfaces. Large mammal flies, including horseflies and tsetse flies, are highly sensitive to polarized light reflected from the coat of a potential host, and stripes appear to interfere with this signal in a way that makes zebras significantly less attractive landing targets than solidly colored animals. Given that the diseases carried by biting flies in sub-Saharan Africa represent a significant mortality risk, this is not a trivial advantage. The predator confusion hypothesis is the one most directly relevant to what happened in our chase. The idea here is that the stripes create a specific visual effect when multiple animals are moving at high speed together, a kind of perceptual chaos that makes it difficult for a predator to track a specific individual within the herd. The visual system of a lion, like that of most predators, is highly tuned to tracking individual targets. Once a predator has locked onto a specific animal, it follows that animal's trajectory and adjusts its own path to intercept it. But if the visual system is receiving ambiguous information about where one individual ends and another begins, if the stripes of one animal blend into and confuse the stripes of the adjacent animal as they run, the lock becomes harder to maintain, and the precision of the interception degrades. The specific visual effect is called flicker fusion. When striped objects move quickly past a fixed point or a fixed observer, the alternating light and dark stripes create a flickering effect that, at certain speeds, causes the visual system to lose the ability to distinguish the stripes as distinct objects, and instead perceive them as a merged, shimmering field. In a herd of zebras running at full speed, this effect may create a visual environment for a pursuing predator in which clear targeting of any single animal becomes genuinely difficult. Not impossible, but difficult enough to degrade the precision of the attack by a margin that, over evolutionary time, has meant the difference between surviving a hunt and not. And then there is the individual recognition question, which flips the logic around in an interesting way. The stripe patterns of individual zebras are unique, like fingerprints. No two animals have exactly the same arrangement. Within a herd, zebras recognize each other by their stripe patterns. Mothers recognize their foals. Animals recognize their social partners. The unique pattern that helps predators fail to distinguish individuals within the herd is simultaneously the identification system that allows zebras to function as a coherent social group. The same feature serves both purposes, which is the kind of elegant evolutionary solution that, when you actually sit with it, makes you feel the deep strangeness of a world shaped entirely by selection pressure over millions of years. So here is our specific zebra in the specific situation that nearly ended its life by inches. Let us reconstruct what happened as fully as the evidence and the biology allow. The three lions had been watching the herd, not from close range because close range is too risky. Zebras have wide-angle vision that covers most of the space around them, leaving only a narrow blind spot directly behind, and their sense of smell and hearing extend their effective detection range well beyond what their eyes alone cover. The lions were positioned with the wind in their favor, downwind of the herd so that their scent was not carried to the prey. They were low, using whatever cover existed, grass, a termite mound, a shallow depression in the ground to break their silhouettes. And they were patient because patience is not a learned virtue for lions, it is a physical state they inhabit as naturally as breathing, the muscle tension of a predator holding itself still against every instinct toward movement. The herd was grazing. Some animals were alert, heads up, scanning. Others were focused on the grass, pulling at it, taking in the calories that fuel everything. This is the state that makes prey vulnerable, not inattention exactly, because even a grazing zebra has one part of its sensory system allocated to threat monitoring, but the divided focus of an animal trying to do two metabolically expensive things at once, eat and watch, and unable to give either its full attention. One of the lions moved, not a charge, not yet, a repositioning, a shift that put the lion in a slightly different geometry relative to the herd, or perhaps a response to a slight shift in the wind direction. One of the zebras at the edge of the herd caught something, not the lion directly, not yet, but something, a change in the quality of the light, a vibration through the ground that was not quite the rhythm of the other herd members moving, a smell that was not grass and not the scent of other zebras. Something. The alarm signal in a zebra is not a sound, at least not primarily. It is a posture. The head comes up sharply, the body stiffens, the ears orient toward the source of the disturbance. And in a herd of social animals that have evolved specifically to use each other's behavior as information, this posture change propagates through the group faster than any vocalization could. Before the first zebra has fully processed its own alarm, the animals next to it are already responding to its response, and the animals next to them are already responding to that response. And within a fraction of a second, the entire herd has gone from divided attention grazing to full alert, every sensory system engaged, every body angled toward the question of where the threat is and which direction to run. And then the lions committed. The commitment of a lion from stalk to charge is one of the most astonishing things in nature to witness, not because of the speed, which is extraordinary, but because of the totality of it. One moment there is a large cat moving with deliberate, controlled stillness. The next moment there is a 200-kilogram animal accelerating toward its top speed in a distance of 2 or 3 body lengths, driving off hindquarters that generate more force per stride than almost anything else that walks on 4 legs in Africa. The initial acceleration of a lion is comparable to that of a top-tier sports car, 0 to 50 kilometers per hour in the first second or two, and the transition from stationary to that speed happens with a smoothness and a suddenness that the prey animal's nervous system has to respond to faster than it can consciously process. The 3 lions came from different angles. This is the critical piece of the geometry, the piece that nearly made the difference between life and death for this particular zebra. One lion came from the front left, angling to cut off the most obvious escape route toward the open plain. One came from the right flank, where the herd's natural tendency to scatter in multiple directions might funnel individuals into the waiting attack. And the third, the one that came closest, came from behind and slightly to the left of the individual zebra that had raised the first alarm, the one that found itself in the most compromised position because it had been on the edge of the herd nearest to the original stock position. The herd exploded. This is the right word for it, not dispersed, exploded. Animals going in multiple directions simultaneously, the massive bodies fragmenting into individual trajectories at a speed that creates, for a predator trying to track a single target, a visual field of extraordinary complexity. The stripes blurred and separated and recombined as animals crossed each other's paths. Dust rose. The sound of hooves on the dry savanna floor was a continuous thunder that resolved into no individual rhythm. Our zebra ran. The first stride of a zebra's flight response is already at near maximum effort, powered by the sympathetic nervous system's flood of adrenaline into a musculoskeletal system that, in prey animals that evolved under persistent predation pressure, is built to go from 0 to survival speed as fast as physics permits. There is no warm-up. There is no gradual acceleration. There is grass and grazing, and then there is full flight, and the transition between them is measured in milliseconds. But the lion behind and to the left was already moving, already close, and the lion's initial burst of acceleration over the first 15 or 20 meters is faster than the zebra's. This is the window. This is the interval during which a lion that has gotten its stalk right can close the remaining distance between itself and its target before the target's superior stamina starts to matter. If the lion can make contact, can get a paw onto the zebra's hindquarters or its shoulder, can use its mass and momentum to throw the zebra off balance at full speed, the chase is effectively over. If the zebra can get past that window, get into the phase where its cardiovascular endurance and its stride length and its agility start to neutralize the lion's raw acceleration, the odds shift. The lion reached out. This is not metaphor. In the video footage that captured this moment, you can see it. The extended foreleg, the reaching, grasping paw with its retractile claws extended, making contact with the zebra's hindquarters. Not gripping, not hooking, but touching, brushing, close enough that the sound of claws on hide was audible to the person who filmed it. Close enough that the zebra's body registered the contact and absorbed it into its flight path without losing the fraction of a second that would have allowed the grip to establish itself. Inches, the claws caught air where flesh had been a tenth of a second before, because the zebra's hindquarters had pistoned forward in the next stride exactly as the contact was made, and the stride was just long enough, and the timing was just close enough to right, that the grip that would have ended everything simply did not have enough material to grip. The lion's momentum carried it forward through the space where the zebra had been. The lion's own recovery from the missed strike cost it the next fraction of a second, the brief period of rebalancing that a quadruped experiences when a full extension-reaching movement fails to make purchase. And in that fraction of a second, the zebra opened a gap. The second lion on the right flank had read the trajectory of the fleeing zebra and adjusted its own angle of interception, angling across the savanna to meet the zebra at a point further along its projected path. This is the intelligent part of coordinated lion hunting, the part that is not so much communication as it is geometry. If one lion is pushing the prey in a certain direction, the other lion does not chase from behind but angles to where the prey will be. But the zebra did something that disrupted this interception geometry. It turned. A zebra at full speed making a sharp directional change is one of the most mechanically impressive things a large mammal does. The physics of it are demanding. At 60+ kilometers per hour, a body of several hundred kilograms carries enormous momentum in its direction of travel. Redirecting that momentum requires not just muscle force but the structural integrity to transmit that force through the skeletal and ligamentous system without damage, and the traction on the surface to prevent the hooves from slipping as they bite against the direction of travel to redirect the body. The legs of the zebra are built for this. The ligaments and tendons of the lower leg in particular are engineering achievements of biological construction that allow force direction to change rapidly without the catastrophic failure that such changes would cause in a less well-engineered structure. The turn was sharp, maybe 20–25 degrees to the right, enough to change the zebra's projected path significantly, enough to change the geometry of the second lion's interception angle from favorable to neutral. The second lion adjusted, but adjusting costs time and distance, and by the time the second lion had corrected its angle, the zebra had covered enough ground to change the picture again. The third lion had positioned itself to cut off the direction toward a thicket of acacia scrub at the edge of the open plain, anticipating that a fleeing zebra would naturally seek cover if cover was available. This is a correct anticipation in general. Zebras and other prey animals do use cover as part of their escape strategy, changing direction toward terrain that will reduce the lion's speed advantage, narrow corridors between vegetation that disrupt coordinated pursuit, anything that makes the geometric envelope of the attack less clean. But this particular zebra, having already made one sharp directional change, was now running a trajectory that passed between the third lion's position and the acacia thicket, a line that brought it close to the third lion but not directly toward it, and gave the third lion an angle that was not quite head-on and not quite flank interception, but something in between, an angle from which a strike was possible but not from the ideal position. The third lion launched, not a full commitment interception run because the geometry was not quite right for that, but a short explosive burst toward the line of the zebra's travel, an attempt to be in the right place at the right moment. And again, the measurements of the outcome were in inches and fractions of seconds. The lion's strike fell short, or rather fell behind, as the zebra's pace carried it past the point of contact a moment before the moment arrived. And then the zebra was through, past all three, in open ground running. The chase continued for another 30 or 40 meters because lions do not immediately accept failure, but the physics of the situation had shifted irrevocably. The zebra was now in the phase of the encounter where its stamina was the determining variable, and while a lion can sustain its top speed for a meaningful distance, it cannot sustain it for the distances that a zebra can sustain near maximum effort. The lion's cardiovascular system, powerful as it is in the explosive phase, is not built for prolonged aerobic effort at high intensity. The zebra's is. The energy systems that fuel sprinting are anaerobic and produce lactate that accumulates and degrades performance quickly if the effort is not converted to aerobic work. A lion that has not made a kill in the first phase of a chase is burning through its anaerobic reserves and accumulating the metabolic debt that makes continued high-speed pursuit increasingly costly and eventually impossible. One by one, the lions peeled off. The geometries of pursuit that had briefly made capture seem inevitable were gone, dissolved back into the flat mathematics of three tired predators and one faster than they'd expected prey animal with open ground ahead and nothing behind it anymore. The zebra ran until the running was no longer necessary, and then it stopped, and that is where the biology gets strange and worth dwelling on. You might expect a prey animal that has just survived a near-death experience by a margin of inches to take some time to recover psychologically, to remain in a state of high arousal, to be jumpy and anxious for hours, and it is, briefly. The hormonal profile immediately following a predator encounter includes elevated cortisol and adrenaline and all the physiological markers of acute stress. But those markers begin to clear in zebras and other prey animals with healthy nervous systems remarkably quickly. Within minutes to hours, not days. Within a time frame that, if we are comparing to human trauma responses, seems almost impossibly short. This is not because zebras have less acute nervous systems than we do. It is because they have appropriately calibrated ones. A zebra that remained in full stress response for days after every predator encounter would be unable to eat, unable to sleep, unable to function as a grazing animal in a landscape where predator encounters are not rare events but regular features of the environment. The nervous system of a prey animal has evolved to discharge the stress response fully and quickly to return to baseline as efficiently as it mobilized, because staying in the baseline state is not a luxury. It is a necessity for survival just as much as the ability to mobilize for threat is. There is a well-known observation by the biologist Peter Levine, who developed a significant body of work around trauma and the nervous system, that prey animals in nature rarely appear to develop what we would call post-traumatic stress responses from predator encounters, even from encounters as close as the one our zebra just had, precisely because their nervous systems discharge the mobilization energy fully after the encounter. Through a shaking and trembling response that is physiologically distinct from the fearful trembling of an ongoing threat, and that appears to represent the nervous system completing the stress cycle that was initiated by the threat. After the predator is gone, the prey animal trembles, and then it stops trembling, and then it goes back to grazing. This physiological discharge cycle is increasingly interesting to researchers studying human stress and trauma responses, not as a direct prescription for human behavior, because human nervous systems are far more complex and human social and cognitive factors create layers of complication that have no direct zebra equivalent. But as a window into the fundamental biology of what a stress response is for and what completion of that response looks like when the nervous system is allowed to complete it naturally. But let us return to the savannah, because the question that is now sitting in the room, the question that the near miss raises and that the biology of the three lions raises equally is this: what actually determined the outcome? If we pull back to the widest possible view, was it luck? Was it skill? Was it the accumulated experience of that particular zebra in that particular landscape? Was it some feature of that individual animal's physiology that made it fractionally faster or fractionally more agile than an average zebra? Was it a mistake by one of the lions, a slightly mistimed commitment, a fraction of a second's hesitation? Was it all of these things at once, combining in a way that no single factor explains? The honest answer is yes, all of it, simultaneously and inseparably. And this is the thing about close calls in nature that makes them so much more interesting than simple predator versus prey narratives allow. Every outcome in an encounter like this is the product of an almost incomprehensible number of variables that have been accumulating for the entire life of each animal involved. Variables that track back through every previous encounter each animal has had, every injury and near miss and successful hunt and failed hunt, every developmental experience that shaped the nervous system and the musculature and the behavioral tendencies of each individual. Every feature of the specific landscape and the specific conditions on the specific day, the angle of the sun and the direction of the wind and the moisture content of the soil and the length of the grass and the distribution of the rest of the herd, all of it converging in 4 seconds of movement that ended with a margin of inches. The three lions had a history that led to this specific arrangement of their positions relative to the herd. They had learned from experience how to coordinate. They had developed, over the course of their lives together, an intuitive geometry of group hunting that placed them in roughly the right positions relative to each other and relative to the prey. But they had also presumably made small errors in their positioning or their timing that created the gaps the zebra found, the fraction of a degree in one lion's approach angle, the fraction of a second in another's commitment to the strike, the slightly off geometry of the third's interception. Whether those errors were themselves the product of the day's conditions, of fatigue from a previous hunt, of the specific disruption of the herd scatter that made target selection difficult, we cannot know, but they were there. They had to be. The inches the zebra survived by were the inches that those small errors created. And the zebra, this individual zebra, had its own history, its own accumulation of experience that shaped how it responded in those 4 seconds. Did it recognize the specific pattern of threat from 3 angles and respond with an instinctive directional strategy? Probably not consciously. But the directional change that disrupted the second lion's interception geometry was not random. It was not the sort of direction that would have been chosen if the zebra were simply running away from the immediate sensation of being chased. It was a turn that created space relative to multiple threats simultaneously, which either reflects a sophisticated real-time threat mapping ability that we would find surprising, or reflects a deeply ingrained behavioral pattern that natural selection has built into zebra flight responses specifically because that pattern is effective against coordinated predators, or most likely, some combination of both. There is research suggesting that zebras and other prey animals do track multiple predators simultaneously during pursuit, maintaining a spatial model of the predator positions relative to their own trajectory, and making directional decisions that reflect this model rather than simply reacting to the nearest immediate threat. The neural architecture that supports this kind of multi-threat tracking is not simple. It requires the simultaneous maintenance of multiple moving reference frames, the integration of that spatial information with proprioceptive information about the animal's own position and speed and the terrain under its hooves, and the continuous updating of projected interception points as all of these variables change. The fact that this computation apparently happens at some level in the nervous system of a fleeing zebra in real time at full speed under the maximum sympathetic arousal of a genuine survival situation is staggering when you actually let yourself think about it. The brain of a running, fleeing zebra is doing something that, if we tried to implement it artificially, would require sophisticated sensor arrays and significant computing power. And it is doing it with a biological neural network that weighs less than a kilogram, running on glucose and oxygen delivered by a cardiovascular system that is simultaneously managing the demands of maximum aerobic effort, maintaining the thermal regulation of a body, generating enormous amounts of heat through muscular work, managing the hormonal environment of acute stress response, and keeping the whole animal upright and directionally stable on terrain that varies stride by stride. The zebra's brain is doing all of this at once, and doing it well enough that the animal survives. This is what animals are, not simple, not automatic, not the naive biological machines that some earlier frameworks of animal behavior described. Complex, adaptive, experience-modified, neurologically sophisticated systems that have been shaped by billions of years of evolution to solve specific problems in specific environments with extraordinary effectiveness. The problem the zebra solved that day, the problem of not being eaten by 3 coordinated predators over approximately 4 seconds of high-speed pursuit across complex terrain, is a hard problem. It solved it by inches, but it solved it. Now let us go deeper into what the Mara is, because this encounter did not happen in a vacuum. It happened in one of the most ecologically complex and biologically rich landscapes on Earth. And understanding that landscape is essential to understanding why encounters like this one are simultaneously possible and improbable, why the drama of predator and prey plays out there with an intensity that exists nowhere else quite the same way. The Masai Mara National Reserve in southwestern Kenya along the border with Tanzania is part of a larger ecosystem that includes the Serengeti National Park on the Tanzanian side. And together these two protected areas form the Serengeti Mara ecosystem, one of the largest and most intact grassland savanna systems remaining on Earth. The specific feature that makes this ecosystem unlike any other is the Great Migration, which is not one event but an ongoing, year-round movement of animals across the ecosystem, following the rains and the fresh grass that the rains produce, covering distances of up to 3,000 kilometers in the course of a year. The plains zebra is one of the 3 primary species of the Great Migration. The wildebeest are the most numerically dominant, somewhere between 1 and 2 million animals moving as a collective, driven by the same fundamental imperative: follow the grass. Thompson's gazelles are the 3rd major component. And the zebras, perhaps 200 to 300,000 of them in the broader Serengeti Mara system, move with the wildebeest in a relationship that is neither incidental nor simply coincidental. Zebras and wildebeest feed differently. Zebras are grazers that prefer the longer, coarser grass, the upper stalks and leaf blades that a wildebeest mouth is less well suited to handling. Wildebeest prefer the shorter, more nutritious grass closer to the soil. So a landscape grazed by zebras in the lead wave of the migration becomes a landscape that is more accessible and more nutritious for the wildebeest that follow. The 2 species effectively process the grassland in sequence, each one making the resource more suitable for the other's particular digestive system, and the result is a facilitative ecological relationship between species that appear to be competitors but are actually making each other's lives better. This mixed herd grazing pattern also has consequences for predator detection and predator avoidance. A group of zebras and wildebeest together has more eyes and more sets of ears and more noses than either species separately, and the 2 species have different sensory strengths, zebras with their particularly acute hearing and wildebeest with an apparently strong ability to detect distant movement in open grassland. The mixed herd is therefore a more effective early warning system than either species could be alone, which is one reason why the association between the 2 species tends to be maintained even in contexts where the direct grazing facilitation benefit is not immediately at play. The lions of the Mara are among the most studied lion populations in the world, with some research projects running for decades and individual animals known and tracked through their entire lives. What the long-term data from these studies reveals is a picture of lion society and lion hunting behavior that is considerably more complex and more variable than the textbook description allows. Different prides have different hunting specializations. Some prides are exceptionally competent buffalo hunters, an enormously dangerous prey item that requires both group coordination and individual bravery of a high order. Others specialize in wildebeest during the migration season, when the numbers are overwhelming and the energy cost per kill can be very low. Others maintain a broader generalist strategy, hunting whatever prey is most available. The 3 lions in our encounter were most likely young males or a coalition of subadults, because the hunting strategy they employed, 3 males working in loose coordination, fits the typical pattern of male coalition hunting in the Mara, where young males who have been expelled from their birth pride often form coalitions of 2 to 4 animals, and cooperate on hunts that they could not successfully complete as individuals. These coalitions have a survival function that goes beyond hunting. Male lions in coalition are more successful at competing for territorial access, and eventually, for takeover of prides and the mating opportunities that pride residence provides. The hunting cooperation they develop as young coalition members is both a survival strategy and a rehearsal for the social and competitive challenges they will face as they mature. A 3-male coalition hunting zebra is taking on a prey item that is genuinely dangerous. We mentioned the kicking force of a zebra's hindquarters earlier, and it is worth returning to this point, because the 3,000 Newton kick of a cornered or partially captured zebra is not an abstract statistic. It is the reason that lions show measurable preference for attacking zebra from behind and attempting to bring the animal down quickly by getting a grip on the throat or the muzzle to control the head and collapse the windpipe, rather than allowing the attack to become a prolonged struggle in which the zebra's rear legs have space to operate. A zebra kick to the skull of a lion has killed lions. A kick to the ribs has broken the structural integrity of a rib cage and caused internal bleeding that kills slowly over days. The risk is real. Young coalition males learning to hunt zebra are not just developing technique. They are learning to manage a genuinely life-threatening hazard as part of their occupation. The miss that occurred in our encounter, the reaching paw that found air instead of hide by a margin of inches, was also a safety event for the lion, in the sense that a lion's extended foreleg at full pace makes the lion momentarily vulnerable to the zebra's kick if the engagement becomes confused. The biomechanics of a lion's reaching strike require a specific body position that exposes the skull and the foreshoulders to counterattack from the prey's rear legs, and a zebra that is running at full speed and has an experienced and powerful kick response does not distinguish between a lion that has gripped it and one that is in the process of reaching. Both positions of the lion are potentially within range of the response. This mutual risk is part of what makes the encounter between lions and zebras so dynamic, so non-deterministic, so full of the possibility of outcomes other than the obvious one. The predator is not in a position of pure dominance relative to the prey. The hunt is not simply a matter of the lion deciding to eat and the zebra deciding whether or not to cooperate. Both animals are at risk. Both animals are making, at some neurological level that need not be conscious to be real, assessments of cost and benefit that shape the intensity and duration of their commitment to the encounter. A lion that has just missed a strike and been briefly destabilized by the momentum of the miss. A lion that is now burning anaerobic energy reserves chasing a zebra that has opened a gap, and is now in the phase where the zebra's cardiovascular endurance starts to be the relevant variable. That lion is making a cost-benefit calculation, not with spreadsheets and not consciously, but at the level of the nervous system and the metabolic signals that the body sends to the brain about effort and depletion and the marginal probability of success. At some point, that calculation tips from continue to abandon and the lion peels off and the hunt is over. The zebra does not analyze this. The zebra runs until running is no longer the appropriate response and then it stops running. And then the shaking comes if it comes, and then the shaking stops, and then the herd reassembles from its scattered trajectory, animals finding each other by sight and by sound, the social bonds of the group reasserting themselves over the disruption of the flight, and within a surprisingly short time the herd is grazing again, calm, present, alive. The grass is still there, the lion is somewhere else. The sun is moving in its arc across the sky. The inches that saved this particular animal are already in the past, irretrievable, a closed chapter in the story that evolution keeps writing across every generation of every predator and every prey animal in this landscape. The story has no moral in the human sense. It has no protagonist in the human sense. It has only the ongoing negotiation between animals shaped by deep time to kill and animals shaped by deep time to not be killed. A negotiation conducted in real time, in real bodies, on real grass, under a real sun, by real